This is a test of recording volume. 1, 2, 3, 4, 5, 6, 7, 8, 9.
This is the second part of a three-part video on continuity. In this video, we will discuss the steps required for full credit to prove a function continuous at a point. Remember, you can't say a function is continuous because it can be drawn without lifting your pencil. We can, however, use the two theorems described here. The first one tells us that polynomial functions are continuous everywhere. The next theorem gives us a list of functions that are continuous on their domain. What does it mean for a function to be continuous on its domain? It means that the only places where a function is discontinuous are at x values where the function is undefined. This means that for all the functions that are on this list, we don't have to deal with the limit. To find points of discontinuity for functions that are on this list, we only need to find x values that make the functions undefined. There is one function, however, that is not on the list, that we must go through the three parts of point continuity in order to prove that it is continuous at a point. It is the piecewise function. Let's try an example. Prove the function f of x is equal to the sine of 2x minus 1 is continuous at x equals 3. Since f of x is a trig function, it is continuous everywhere that it is defined. If we replace x with a 3, we get the sine of 5, which is defined. F of x, therefore, is continuous at x equals 3. In this next example, prove the function g of x, which is equal to the natural log of x, is continuous at x equals 0. Logarithmic functions are continuous on their domain. However, the natural log of 0 is undefined. So g of x is discontinuous at x equals 0.
Prove that h of x is continuous at x equals 2. Because h of x is a piecewise function, we need to verify the three parts to point continuity. The first part requires us to show that h of 2 is defined. We use the bottom equation when x is greater than or equal to 2. Plugging in 2 gives us 0, so we know that it's defined. The second part requires us to show that the limit as x approaches 2 exists. This means we need to find the left-hand limit and the right-hand limit. When x approaches 2 from the right side, all the values of x are greater than 2. We use the bottom equation when x is greater than or equal to 2. Plugging in 2 to solve the limit, we get 0. Now the left-hand limit. As x approaches 2 from the left side, all the values of x are less than 2. We use the top equation for values of x less than 2. Evaluating the limit, we replace x with a 2 and we get 0. Because the right-hand and the left-hand limits are equal, the two-sided limit exists. Now the third part. We need to show that the limit value as x approaches 2 is equal to the function value at 2, which it is. Both of them are equal to 0. Therefore, we can conclude that h of x is continuous at x equals 2. In this final example, we are to prove that p of x is continuous at x equals 1. Again, p of x is a piecewise function and requires us to look at all three parts to point continuity. The first part is to show that at 1, p is defined. When x is equal to 1, the equation we use is the middle equation, 3x. Replacing x with a 1, we get 3. Therefore, the function value at 1 is defined. Now we need to show that the two-sided limit exists. We do this by showing that the right-hand limit and the left-hand limit are equal to each other. As x approaches 1 from the right side, all the values of x are greater than 1. We use the bottom equation, 1 over x, for all values of x greater than 1. Evaluating the limit, replace x with a 1, we get 1 over 1, which is just equal to 1. Now the left-hand limit. As x approaches 1 from the left side, all the values of x are less than 1. We use the top expression for values of x less than 1. Evaluating the limit, replace x with a 1, we get 2. Now, the right-hand limit is equal to 1, and the left-hand limit is equal to 2. Because each of the one-sided limits, the left and the right, are not equal to each other, this tells us that the two-sided limit as x approaches 1 of p of x does not exist. Because the limit as x approaches 1 of p of x does not exist, p of x is discontinuous at x equals 1.